A train sets off from a station at time equals to 0. The graph shows how the distance between the train and the station varies with time. So we see that the distance is increasing. So what's interesting about it is it starts at this train station distance. It goes very far from this is the maximum distance it has from the train station. And now it's making its way back to the train station because the distance is decreasing now from the measured train station. So it's coming back. So there are two things over here. They're talking about the speed of the train, the speed, and not really versus, but the speed and the distance. So distance is kind of going down, right? Or it's moving closer to the station again. And what about the speed? The speed is kind of really hard to see, but the tangent would give us the speed. So the steeper this graph is over here, and if it's getting steeper, we'll have an idea that it's speeding up. So over here, we kind of see that it's actually hard to see, but over here, I would have gone with constant, but it's definitely not slowing down. So I would say it's more speeding up. So my best answer is it's increasing in speed and it's moving towards or closer to the station. So our correct answer is D. A horizontal beam is pivoted at X. A mass of 200 grams rests at the beam as shown. So 200 gram is resting, right? The center of mass of the beam is 50 centimeter from the right. Center is 50 centimeters from the TK. So the center is kind of over here. I'll put a small c on top of it. It is here. And TK. The beam is balanced. What is the mass of the beam? Okay, so the mass of the beam is acting over here. And well, it's actually the weight that's causing the moment. So we gotta find out the weight of this first. Let's figure that out. Okay, I guess it's easier said than done. But okay, according to the pivot, there are two moments acting on it. There is this moment, and then there's the moment caused by the weight. This moment is going to be clockwise because it's gonna push it down like this and it's towards the right. So this weight will try to tip it towards the right hand side or clockwise. This will be counterclockwise, so I'll put those signs on top. And we realize that moment counterclockwise should equal to the moment as clockwise. The mass is 200 grams, so the weight over here is going to be times 10, which is 2 newtons. Should have made more room. So it's 2 newtons, which is F times D equals to F times D. This is 2 newtons times 20 centimeter, which is 0.2, times the weight, which is unknown, times the distance, which is this length is 50, this is 60, this has to be 10 centimeter. So times 0.1. So 2 times 0.2 is 0.4. 0.1 times W. W equals to 4. And that's just mg. So I have to divide this by g now to convert it. So I should get divided by 10, 0.4 kilograms, which is 400. 400 grams. The answer is C. Let's undo that. The answer is C. At a depth of D in seawater, the total pressure experienced by a diver is 2P, where P is the atmosphere pressure. At which depth is the pressure 4P? So this is interesting. So here is the surface of the water, and let's mark it. This is, you know, just D. Levels down. This is 2D. This is 3D, and this is 4D levels down. So our driver is our driver, because he crashed into a swimming pool. Our driver is here, and he's experiencing a pressure of equal to 2P. Now he's experiencing the pressure because of the atmosphere. That's P, and probably at this height, this depth of water, you also experience a pressure of P. That's why he's experiencing a pressure of 2P. Right, so combine, it's 2P, P over here, P over here. So if he was over here, let's mark that down in a dotted position. If he was here, he would experience a pressure of 3P. And over here, he will experience a pressure of 4P. Question is asking, at which depth is the pressure 4P? Well, it's going to be at 3D. Q. Which statement about water is correct? At the boiling point, water vapor molecules have the same kinetic energy as the liquid water molecules. That's kind of tough to answer. Let's go over point B first. So evaporation occurs only at the boiling point. That's not true. Water can be left as in a puddle, and over time it can evaporate away, so it doesn't have to be at the boiling point. So this statement is wrong. Water molecules become heavier when water freezes. That's actually not true, and possibly the reverse is exactly true, because if you put ice cubes in a glass of water, where are they? In a glass of water, ice cubes will float on top, because they actually become less dense, because water seems to expand just a bit when it's freezing. It's just a quirk water has. So it becomes less dense because it expands and the mass remains the same. So it becomes ever so slightly less dense than the liquid water around it, starts floating. So heavier, I mean, its weight will not change at all, but it does become less dense for a bit. And freezing it even more, it'll just become more dense, then it can sink. Okay, so this is actually wrong, and we know it because we see it. Water molecules lose all of their kinetic energy when water freezes. People might think that's the case, but even in a solid form, water particles are vibrating about their fixed position, so they still have some energy, right? So it's at absolute zero, which is a very low temperature, when all substances lose all kinetic energy and they're just still. Anyway, back to A. So what's our correct answer then? Our correct answer is actually A, because the temperature is giving us the exact measure of kinetic energy of the particle. So be it liquid, be it gaseous, if they're both at the same temperature, they have the same kinetic energy. So our best answer is actually A. This type of question in particular is difficult because we think they're talking about the critical angle, but they're not. So the equation we kind of study is difficult to kind of use over here. So we'll try our best to kind of use it properly. So the equation we have right now is, what we're going to use is sine of incident over sine refracted is equal to refractive index of the light in a vacuum divided by refractive index in the liquid, right? Air and liquid. So I say vacuum over here because the refractive index of air and vacuum are very similar. And yeah, so let's do that. So actually, yeah, it's vacuum incident. Yeah, I think we're okay. Sine I want to find out. So I'll leave it as it is. Sine of I divided by sine of R. R is actually this angle, which is equal to 90 minus 32. 90 minus 30 is 60. That makes it 58 degrees, equals to refractive index of a vacuum is 1, and refractive index of this liquid is 1.4. So let's calculate that real quick. So I'm getting 37.2, and yeah, that's very close to our value over here. So the correct answer is B. Okay. A ray of red light in air enters a semicircular block. Which diagram shows the partial reflection and the reflection of the ray? Okay. So if total internal reflection is any help, we know that from a denser medium, this is more dense. If light is traveling in a denser medium and goes out to a less dense medium, it will bend, you know, towards, or not towards, away from the normal, away, right? So that's not really happening here. That's not happening here, and it's happening here. So this part is correct. So I like this part. Let's get a better highlighter out. I like this part. I like this part. Now what about the ray that's on the inside, right? So there's two elements. This light is coming in. One is being refracted out. So it should move towards it. So we identified the correct ones. What about this one? So if it's being reflected, laws of reflection will apply, and it has to be the incident angle should match the reflected angle. So that's happening over here and over here. So correct answer is just straightforward. D is our answer. White light enters a prism and forms a spectrum. The rays in the air are labeled. Which diagram shows how the white light is dispersed by the prism? So what happens is, white light is made up of 7 different types of light, colors of light, and they're mixed together, so we see it as white. And what happens is, as soon as it starts to refract, each light, what it's made of, what white light is made of, refracts, because all of them have different speeds. They refract at different rates. So as soon as they start refracting, they start spreading out because they have different speeds. So over here in C, we see that's already happening, and that's true. It's happening, and it's kind of happening more over here. So I like that, and it's also happening over here as well. It's also happening over here as well. ठीक है. But what's wrong over here is that needs to be on top and violet needs to be at the bottom. So the correct answer is C. Okay, which diagram shows the pattern and direction of an electric field lines near a positive charge? And I don't know why. I think people might confuse this with the right-hand rule, but yeah, A is the obvious choice. Electric field lines go from positive to negative, and that's essentially it. So our correct answer is A. A 100-watt lamp is switched on for 5 hours each day for 3 weeks. The cost of 1 unit of electricity is 0.24. And how much does it cost to run the lamp, this particular lamp, for this amount of time? 3 weeks, 5 hours daily. Right, so we have to calculate the price. So we want to figure out how much is a unit of electricity. So unit is the same as 1 kilowatt hour. Right? It's essentially 1 kilowatt hour. What's a kilowatt hour? It is the energy used. It is the energy used by a 1 kilowatt appliance, a lamp, anything, in 1 hour. So in joules, it's exactly. So how did I get this value? I took 1 kilowatts, multiplied, and this is per second, right? That's joules per second. So I multiplied it by 3600 to get, that's how many seconds there are in 1 hour. So that's how many joules we're talking about when we're talking about 1 kilowatt hour. Why don't we use joules and why do we stick to kilowatt hours? It's just easier for, people who like electrical, people with the power company. It's just easier for them to use this because this is just a weird number. You know how we kind of end up using moles? You can say 6.2 times 10 to the power 23 atoms, or you can say 1 mole of atoms. It just makes 1 mole easier. It's that dozen argument again, right? So 1 kilowatt hour, that's just the norm. So we have to kind of get an answer in terms of norm. So if I have so this is what a 1 kilowatt hour is. I have one kilowatt hour of energy is equal to 1 kilowatt appliance running for 1 hour. But what if I had a 0.1 kilowatt lamp? So this 100 watts is essentially 0.1. Wow, 0.1 kilowatts, right? That's what 100 watts is. So if I ran that, so if I just use that, my life will be a lot simpler because I can figure out the price very easily. If 1 kilowatt hour is equal to 0.24, 0.1 kilowatt hour will be equal to 1/10 of this, 0.024, right? So I'm just trying to make my calculation a little easier because I have good understanding of kilowatt hours and kilowatts. So why not do that? So this lamp has a kilowatt hour rating of 0.1. So it'll consume this much. We just talked about this, 0.1 kilowatts because it's 100 watts. So in 1 hour, it'll use the same amount of energy as 0.1 kilowatt hours, right? It's running for 5 of those hours, 7 days a week for 3 weeks. So 0.1 kilowatts times 5 times 7 times 3 gives you 10.5 kilowatt hours. That's the total amount of energy used. And if you want this in joules, you can just multiply it by 3600 and you'll get some value like this. Probably like with 2 more zeros because it's in the tens, 1 more zero, right? Now we take this value and we know 1 kilowatt hour is $0.24. How much is this? So it's going to be very close to just 10 times the amount, slightly higher. So I can just go for an answer like that. That's 10 times the amount and slightly higher. But if I calculate it, I get that exact value, which is $2.52. The diagram shows a current carrying conductor between the poles of a magnet. The force on the wire acts downwards. So the force is acting downwards. So let's figure that out. It's acting downwards. That's the force. And the arrow is telling us how the current's behaving. That's kind of like current needs to be blue. That's where the current is. So if I use my left hand rule, it's telling me that the magnetic field needs to be going like that. So magnetic field and of course the current. Now 4 changes are possible. You can increase the current, stronger magnet, so increase the magnetic field, current can be reversed, and the pole exchanged. Which 2 changes made together keep the force acting downwards? The obvious answer is 1 and 2, because if you increase the current, that'll just make the force stronger, and if you increase the magnetic field, that'll also increase the force, so it'll stay downwards. So 1 and 2. But if we look at the answer, there's no 1 and 2 option, right? So it has to be some other combination. There's no 1 and 2 over here. So let's look at if the current is reversed. If it's like that, the left-hand rule will be rearranged. Will be if the current is reversed and the magnetic field is still horizontal, so the force will have to be upwards. That's what your left hand rule is telling you, right? And so just using 3, reversing the current will reverse the direction of the force. But if you also change the poles at the same time, so over here, if I change the poles, if I take it away from here, something's gonna happen to the force. I'm removing that as well. So if you change the poles now, reverse the direction of the poles, which way is the force now going to add? So it's like a double negative, right? You're changing 2 things that make the force go opposite. So once the first time you just switch something, it points upwards, but the second time you do it, now it's pointing downwards, and that satisfies our left-hand rule as well. So the combination of 3 and 4 does the job, and that's our answer, D. In an alternating current generator, a magnet rotates near a coil of wire. The induced electromotive force in the coil is displayed in an oscilloscope. Which trace is produced when the magnet slows down? So what's going to happen is, for 1 complete rotation, a magnet makes 1 complete sine wave, right? So for 1 complete rotation, it's doing that. So the faster it does per second, it'll have more of these per second, and the slower it does it, it'll be slower. So over here, you see it rotating, so to speak, fast, and now you see it slowing down. Now it's slower and slower, because for a given time, or it's taking for it a lot longer to complete 1 complete oscillation. So B is our most likely candidate. But what's also is happening, because it's slowing down, it has less energy, or it's resisting the magnetic field less, right? So that also influences the magnitude of the current being generated. So if you're rotating very slowly, not only is the sine wave being generated, or the alternating current being generated of very low frequency, you're not really putting too much energy, because to spin it really fast, you have to kind of fight it, because as soon as you start rotating it, a current will be induced in the coil, and the more you rotate it, the harder it is to rotate it more, because it's fighting the magnetic field, right? And the faster you do it, you're essentially putting a lot more energy into it. That's why the amplitude also rises. So our correct answer is actually D. The list shows 4 physical properties. We have mass, resistance, voltage, and volume. How many of these properties can be used to measure the temperature? Let's say you have like a metal wire at a particular length, right? You put 2 nodes at it in a corner, and you connect that to some sort of device that can measure, the current or something, right? Or let's start with some mass. Let's skip that. Let's look at resistance. If this thing is a ohm meter, right, and the more you heat it, there will be a change in resistance, and you can use that change in resistance to, if you have a chart or something, or if you know, to predict what the temperature of that device is, or like change to. Is it, at least you can tell if it's higher or lower, right? Same with voltage. If you put like, a voltmeter around it with like let's say a battery, and the wire will have some internal resistance, and if it's changing that, the voltage about the entire thing can change, right? And that will also be as measurable as the resistance is, right? What about volume? When you heat something, it expands, and if you can measure that change in it's very hard, because it's it's a very maybe not very hard, but it's not really done a lot because it's just a silly thing to do, I guess. But if I give you, let's say, some object that can fit really well into another object, and it's not fitting anymore, what can you deduce about the temperature? You'll probably say that thing is probably a lot hotter than it was because it can't fit into that object anymore. So volume can also indicate that the temperature, there's a difference in temperature, even higher and lower. But mass is uniform, like it's universal, right? You can't really have anything change something's mass unless you add more stuff to it or take away stuff from it. So mass is something that just does not change for anything. So our correct answer is just C. In which optical instrument is the distance between the object and the lens less than the focal length of the lens? So if I keep it here like that, this diagram, over here we see the object is here, and the horizontal line touching the lens and being refracted will be towards the focal point, and the one going through the center goes straight, and these rays will never meet, so we have to trace them backwards, and we see that they kind of meet here. So that's where our image will form, right? So our image will be somewhere here in red, like that. And so the characteristics of the image are that it is upright and enlarged, and of course virtual. So it's not real, but you can see it. And yeah, so camera needs to form an actual image. Something needs to be there on the screen for it to form. So this is bad for a camera. For a magnifying glass, this is actually ideal. So not only is the image not rotating, it's a real image, it's actually, sorry, it's not real. It's like in the right orientation. It's virtual, but you can still see it, and it's larger. So yeah, so magnifying glass is like, yep, very happy with this sort of setup. And you have to kind of look really close at a magnifying glass as well, right? And then we have a photographic enlarger. Can that work? Yes, it can. But the problem is a photographic enlarger will project it on some screen. So you probably want this on the other side, the image being formed on the other side, so it can be projected on a screen. So it's going to be very close to some sort of, or at least you want it on opposite sides. So you can keep the object on one side and the other side is processing whatever and however it's enlarging. So it's kind of like a projector anyway. And a projector, I think we just talked about it because it's pretty much the same use case. The projector needs to be an actual image on the other side so the image can form. This is actually not a real image. There's no light over here. It's just that once you have eyes over here, instead of seeing this, you end up seeing this because how the lights are spreading away, right? That's what a virtual image is. You can see it, but it's not really there, so it can never be formed on a screen. So our correct answer is B.